We're really very honored to have Kumran giving us a GTP colloquium. So Kumran was born in Iran. He did his BSc at MIT. Then he went on to do a PhD with Edward Witten, and then joined the Harvard at Princeton. Then he joined the Harvard Society of Fellows, then moved on to a professor position at Harvard and has been there since. Professor Bappa is an extremely distinguished string theorist, very the physicist. His contributions are numerous, but in particular they include the Schrödinger-Bappa counting of black hole entropy. The work he did, in which he used micro constituents to count the number of states and find agreement with the Hawking-Bekenstein entropy, demonstrating that Hawking-Bekenstein counts states and string theory has the ingredients to count. Professor Bappa's work has won many awards, including the Dirac Medal, the Danny Heinemann Prize, and the Breakthrough Award in 2007. Okay, so thank you.
Thanks, Shiraz, for this kind introduction. And as I mentioned in the previous talk, I gave a technical talk. I feel at home here at CIFR because many of my colleagues are here and collaborators and so forth. So it's great to be here. And also, I have been in India for past 2 weeks now, and a beautiful country and very happy to know people. So I hope I'll be able to come in the future as well and be able to interact with you guys. CIFR, I understand, has a long history in our fields in high energy theory, and probably the center of many of these activities in India for our field. So it's a pleasure to give this talk here. So I'm going to talk about connections between quantum gravity and observations to make using that fact, just the fact that gravity is a quantum theory. Not just classical theory of gravity, but quantum theory of gravity, and to connect it to potential observations or predictions for our universe. Now, quantum field theories, if you don't include gravity, are well understood. So, if you just talk about quantum electrodynamics or quantum thermodynamics, we know relatively well what happens to it. We know, for example, in the case of QCD, there's these nice features about the running of the coupling constant, cathodic freedom, confinement, all these features. We cannot necessarily compute everything exactly, but we have nice tools to compute things in a systematic way to any order of approximation we wish, or numerical simulation that if anything else is harder. And the question is, okay, so what do we learn? Well, we know we could kind of say we understand the space of quantum field theories in the sense that we know in principle how we do exact computations in all of it. And perturbative ones at weak couplings, things are described by the beautiful Feynman diagram and all that. We are very fond of these things and long history. Now, to include gravity in the context of Einstein's theory, what we usually do is we start with the quantum field theory and we couple it to metric, to the distance in space-time. And that basically what that means is that we take the same kind of things we do usually, but now imagine possible ripples in space and time. A curvature in the fabric of space-time is coupled in a quantum way. So in practice, what that means is that if you take your action, your Lagrangian might have matter fields like gauge fields, fermions, and so forth, which couple to the metric, and you add the Einstein-Hilbert action in the curvature. So maybe I'll wait till people can comment. There are some people coming from things. So the quantum gravity action basically takes the matter fields interacting with the metric, add to it the Einstein-Hilbert action, and we integrate in the space of fields, matter fields, gauge fields, as well as the metric. So this matrix becomes a dynamical integration over which defines what we mean by quantum gravity. So it seems easy. You just take your Lagrangian and just add an action and just one more integration. Big deal. So what is the big deal about quantum gravity? What is the problem? This approach does not work. It should have worked. It does not work. In fact, when you try to do the same kind of game that Feynman played for quantum field theory to make sense out of the amplitudes, you find that there are infinities that even Feynman could make sense out of. So he tried famously in the 60s, early 60s, he tried to make sense out of quantum gravity amplitude for the fun of it. He kind of made the point that he's just doing it for the fun of it, not because he expected any experiments to be relevant for this. But he failed to make sense out of it. So it doesn't work, sorry. It just was difficult or impossible to make sense out of it the way he had been used to using that formalism for field theories. So the most natural conclusion from this could have been, I'm not saying Feynman said this, but it could have been that gravity cannot be coupled to quantum fields. You never should integrate over the metric. You should just keep it fixed. Well, nobody said that because we know that our universe is like that because gravity for us is dynamical and therefore we cannot have part of the system quantum mechanical and the rest of them not. And therefore, this is not a good solution. There must be a solution of coupling gravity in a quantum way to the rest of the matter. And our universe is an existence proof of this thing. Maybe we exist. So therefore, it should be possible. Well, happy to say that string theory offers a solution to this conundrum. And what is string theory is just replacing point particles by extended objects like strings. And somehow this resolves the problems of infinities that Feynman could not solve within his approach. But viewing the Feynman diagrams as replacing point particles by the corresponding tube strings and the propagations replaced by connected tubes in this form, what we call the worksheet of the strings. So the word lines becoming worksheets and their interactions become these shapes of tubes. You see, this tube is topologically much smoother than these Feynman diagrams, which has these joining and splitting points, which are kind of abrupt. Whereas this splitting and joining of the strings is a smoother process, and that's kind of the reason that these are nicer than particle interactions that Feynman has to deal with. And this turns out to resolve the problems that Feynman had difficulty resolving. Now, it's good. So, but can we get every quantum field theory in this way? In other words, you tell me I want to study, let's say, QED coupled to gravity, or QCD coupled to gravity, or this theory coupled to gravity. Can you do it? Can string theory do this? Well, string theory comes with a very, very specific repertoire of objects. You cannot choose everything you want in string theory. String theory comes with a very specific set of fields. So what can you do to manipulate things to get something you like? Well, one of the good things about string theory, even though it might originally have thought as a negative thing, is that extra dimensions exist. You might say that's a bad feature because we don't see these extra dimensions, at least macroscopically in our universe, we just see these spatial dimensions. So that's a disadvantage originally, but actually it can be turned to an advantage by using it to get new kinds of things in our universe, in the macroscopic two-dimensional one, by taking these extra dimensions and shaping it in the form we want. We just engineer any physics we want out of it. Just choose this shape, that shape, and so on, to get QCD, QED, this, that, whatever you want. So that was the question. Can we do this? Can we engineer different kinds of field theories by taking the shape of these extra dimensions that are quote unquote unwanted, at least macroscopically we don't observe them, and benefit from that form? So we know that there are many solutions to string equations of what these extra dimensions can be, and they give you different things. I mean, this is a famous caricature of what kind of things they could be. Complicated spaces So here the yellow direction denote the macroscopic directions, the 3 spatial dimensions, let's say. And these blue directions denote the internal dimensions, and they could be complicated 6 extra-spatial dimensions, let's say. And they don't necessarily move around like this video might show you. And they may be the same at all points, at least for low energy, they should be the same. But in principle, you can imagine them changing in shape and time and space in principle. And the objects that we deal in our universe, so if you think about now the macroscopic universe as this blue sheet, and the internal geometries, these tiny spaces now are blown up in size to look like this blue donut, or sorry, purple, whatever this color is, pink or purple donut, that you could view as internal dimensions. You could have strings wrapping around them over a given point in space. In other words, you should imagine at every point in space, we have one of these internal spaces, donuts, and you can choose any one of them, these donuts, and wrap strings around them in different ways. And that will give you the particle as viewed from a macroscopic two-dimensional perspective over that point. So you can create new particles by considering different configuration of the strings in different directions. And in addition to strings, there are other objects like membranes and other things which could wrap different cycles and different shapes. You get the rich structure of particles you can see in our space. So this gives rise to a plethora of interesting effective field theories. For example, one shape of these internal dimensions could give you a gauge theory, which is like a QCD, but maybe with one extra rank, let's say SQ4 instead of SQ3 color. Instead of having 3 generations, might have 2 generations of matter. Another one could give you a different group of thing with other representations of matter, and so on. And so the question is, can you choose arbitrary shapes or features to give you arbitrary consistent quantum field theories? Now, the surprise is that it seems we cannot get arbitrary quantum field theories. And indeed, far from it. We seem to only be able to get a finite number of quantum field theories. Finite number. This is a very different thing than we are used to in physics. In physics, we are used to writing a theory, write Lagrangian for example, any gauge group, any kind of forces, SUN, SU3 is QCD. You could imagine instead of 3 colors, you could have N colors. What's the problem? Somehow we find that in string theory, this is not allowed. You have a very specific number of colors. If there's an upper bound of how many colors you could have. That's surprising. For example, if you take the maximal supersymmetric theory in 4-dimensional, which is what's called N equals to 4 supersymmetric theory with matter, that's the maximal supersymmetry if you want to have matter, and ask what is the gauge group, you find that the gauge group cannot have rank bigger than 22. So for example, if you take SU 24 or 25 or 26, anything higher than 23, those are not allowed. They are just inconsistent, and it's not possible to get them. They don't arise in string theory. Now, that's a disappointment maybe, because you say, well, there are all these things. So string theory it's not a good thing then, because it's not giving us all the rest. So at least the set of theories we get from string theory seems to be what we could call measure zero compared to the set of all possibilities. For example, in this case, we get a finite set out of all integers, which is measure zero among the set of all integers. So at least from string theory perspective, we get the impression that if string theory was the only show and tell, a generic quantum field theory cannot be consistently coupled to gravity. If this was the only thing we could do. Now, this raises the question, does the fact that most quantum field theories do not arise in string theory a deficiency of string theory or a general conclusion about consistency requirements of coupling of anything to quantum gravity? Is this a feature of quantum gravity or just a string theory deficiency? Evidence is emerging that this is not a deficiency of string theory, but subtle reasons for consistency of quantum gravity. and connection with basic facts of quantum gravity, such as consistency of quantum description of a black hole, like a unitary evaporation process for black hole, or other features of information content of the black hole, and all these kind of things give rise to a picture which fits very well with the restrictions that we seem to get in string theory. So therefore, we believe that these restrictions of the finite set that we seem to be getting in string theory is not a bug of string theory, but a feature of a consistent quantum theory of gravity. So having said that, we say, okay, if there's a finite set, what is good about this set? It's like these jewels. How do you find these jewels? How do you distinguish them? Where can I find them? After all, we are one of these jewels, probably. Our universe is one of them. And so we want to know what characterizes this set of jewels. So the good ones, we call the landscape, just the terminology, string landscape, or more generally, we could call it quantum gravity landscape. And the bad ones, namely the things that we thought may exist, but actually do not exist, if you include gravity in a dynamical way, we call them belong to a swampland. In other words, they mimic landscape, but they really aren't that good. So we call them swampland. Now, it's much more difficult to say what is good about something if they're a finite set among an infinite thing, but it's much easier to say what is bad. So this gives rise to a program called the swampland program to find the bad ones, or find the criteria which puts you on the bad side. It's not that like we are interested necessarily in bad ones, but that gives you a way to narrow down the possibilities of where you can find these finite jewels. Like it's not on this side of the box, it's not on that side, it's only this corner or something. Once you delimit it like this, you have a better handle of what properties you expect of the good ones. So you could imagine like this is a caricature of this. You have different kinds of possible compactification in string theory. And this gives rise, so this is the ultraviolet completion of the gravity. And in the infrared, you get a finite set of possible effective field theories that it could land on. Or another way of saying is that if you look at the space of all quantum field theories by this green region, most of them are not possibly arising as the low energy description of the quantum theory of gravity, but there are a finite number of them, which I denote here by these blue islands or jewels, for which our universe standard model is presumably one of them. And we want to understand how to get a handle on those. This is, of course, a welcome news. We are part of a finite set of possibilities. We are not that we are egotistic to say we are special. Of course, that's also a good feeling, but that's not what I mean. To say we have a finite set of things allows us predictability. If you're a finite set of possibilities, then you can say something concrete. So therefore, this is basically geared directly towards saying some prediction. Now, the question is, can we use some of the criteria we have found by consistency of goodness without actually finding which universe is our universe to say what general features our universe has? Now, you might say, why are we doing this instead of finding all the finite set? It turns out finding the whole set is complicated and very difficult. So when I say it's finite, I don't mean like 3, 4, 5, no. It could be a huge number, and there are a huge number of ways of getting it, but finite. So I don't want to mislead you to think it's just a few of them, 4 or 5 of them. We just study all 4 or 5 and find which one we are in. No, that's not possible, I'm sorry to say. Nevertheless, the question is, can we put criteria for the bad ones so that we can now use that to say the complement of it should be part of the features of our universe, and that could that lead together with some other observations to new predictions that we can now check in experiments? That's the question. So that gives us this possibility. So in fact, I will just review in this colloquium for the rest of this talk some of the proposed criteria for theories to be in landscape or to avoid being the swampland. There should be in your theory no global symmetries. So quantum gravity does not like symmetries. That sounds strange. We have we teach our students, this is not symmetries. Symmetries are powerful, etc. Well, it's true, symmetries are powerful, makes things much more restrictive and so on. But quantum gravity does not like symmetries at all. In fact, if you have a symmetry, it has to be gauged. By that, it means that the only symmetries allowed have to be accompanied with some electrical fields. You cannot just have a symmetry without coming from some fields. In other words, we can have local symmetries like in Maxwell's theory, that's fine. The number of electrons is conserved is fine. But if an electron did not have an electric field, it would not be fine. So that means that symmetry just by itself is not allowed. Quantum gravity is unique. What that means, I was just telling you there's a huge number of these plethora of these possibilities. What happened? By that I mean that there is no obstruction in going from one to the other in some finite action process. Like for example, here in our universe, we have particular matter content, etc. But you say, you know what? I don't like this particular universe I'm living in. I like a different one, which I know it exists, but it's just not my universe. In principle, there's a process to be allowed to make that universe within your universe in a bubble, in some particular lab setup. Now, it's not to say that I know how to do that, but the quantum gravity tells you there's a finite action process which allows you to construct this. In other words, there's no obstruction to go from one to the other. The quantum gravity vacuum is connected in this sense. There's only unique theory. If you have a gauge theory like electric charges, all the charges appear in your theory. You cannot have, for example, a Maxwell theory with only the even charges appearing or no charges appearing at all. You have to have all the charges appear. You cannot skip charges. Now, in quantum gravity, we can sometimes have some scalar fields which have no potential, and you can give different expectation values, moving their vacuum expectation value. Different condensates are moving around, and it turns out that the range for these fields in a given effective field theory is always finite. You cannot move it to infinitely far away. And if you push them to far away things, something dramatic happens, and your effective field theory should break down. And this is related to the celebrated feature that we have discovered in string theory called duality. So duality conjectures predicts this. A quantum gravity theory must admit higher dimensional objects. It cannot be just point-like objects. It doesn't have to be strings necessarily, but it has to have extended objects. Sometimes the extended object could be a membrane instead of a string. But it has to have some extended object, higher dimensional object. In a quantum theory of gravity, always gravity is the weakest force, just like our universe.
So where does the number 5 come from?
I'm going to come to all of these. I'm just first of all reviewing the statements, and then I come to explain. Gravity is always the weakest force, like in our universe. This is called the weak gravity conjecture. And finally, there seem to be restrictions on critical points of positive potentials. And this has cosmological implication. As you know, we live in a universe where there's dark energy, positive amount, so just like this situation. And it turns out these are one of the hardest cases in theory. And therefore, luckily for us, it might lead to concrete prediction. So therefore, we are in a happy situation where our universe seems to be very difficult to get in string theory. So some very elementary but basic facts about black holes, which I want to remind you. If you suppose you have like in our universe, you have an electric charge, fix a charge Q, and fix a total mass M. Let's work in Planck units. Then as long as the mass M is bigger than the charge, there is a black hole solution with nice features, exists. And the extreme case, without naked singularities, is when M equals to Q. This is the extreme of black. These are some features of our black hole macroscopic objects, solutions to Einstein's equation. Black holes have thermodynamic properties. They carry some microscopic information in them. In particular, they carry an entropy. They signify a number of degrees of freedom proportional to the area of the horizon of the black hole divided by 4, where you measure the area in Planck units. So the entropy of a black hole is equal to 1/4 of the area. These are some of the basic features of black hole, which has nothing incorrect to do with string theory. String theory is an example where it satisfies these conditions, but any potential consistent description of quantum gravity should have these features because it follows from just an infrared effective description of gravity itself. Okay, so now I go over the list of things I told you that the quantum gravity seems to imply and connect it to the features of black hole. There are no global symmetries I mentioned. So suppose you have something like charges like electron with no electric field and throw a conserved charge in a black hole, throw it in. So when you throw it in, after a while, another feature of the black hole I should have mentioned is that the black hole always evaporates to nothing at the end. So if you throw it in the black hole, after a while, the black hole evaporates. Now, as it evaporates, its mass goes down and size goes down. But when it evaporates, from the outside of the black hole, you don't see any electric field coming out because the charge that I threw in carried no electric field. This was not charged by an electrical field. And therefore, from the outside, you get, when it evaporates, you get equal number of plus and minus charge states, because there's no preference between one or the other as it evaporates. And therefore, the evaporation process is neutral in creating a net charge. But you threw in one charge, and there is no imprint of that charge from outside. And therefore, as it evaporates, the black hole loses that charge. And therefore, you lost the charge altogether at the very end. So the black hole evaporation process gives you a way to get rid of that charge. Therefore, the charge is not conserved. That's the black hole argument. Now, this is consistent with everything we know in string theory. In all the string theory examples, we also find that whenever we have global symmetries, they have to be accompanied with a gauge field, like an electrical field. I mentioned the uniqueness of quantum gravity. So if you're not happy with our universe, you can create your own in principle and go into that. Isn't that a nice feeling? So they're all connected. Nobody said, no, this universe does not belong to you. You can never get to it, even with infinite amount of action, you cannot get there. No, there's no such thing. Everything is one soup. You can get from one to the other. And this actually is related to the first point I made. It's related to a general notion of no global symmetries exists. Because suppose in our universe, we have one universe and then there's another universe. I'm saying, no, there's no way you can get from here to there. If it's infinite action process, that means there's no way you could do it. Then you begin to give a quantum, then you can assign a charge based on which classes of things can go to each other and which ones can't. So you can design the notion of a global charge, which I said should not be possible. And therefore, the symmetry not being possible also implies that quantum gravity is unique. That's the basic idea. So here, in the context of string theory, you take as I said, there are extra dimensions. So you can think about the extra dimensions, you compactify it on some manifold. You curl up the extra dimensions into some shape, and somebody says, well, I don't use that shape, I use a different shape. Instead of shape M, I use a different shape N. It turns out that there's a process that can take from any shape to any other shape. In other words, the conjecture is that there's no obstruction in deforming one to the other through some intermediate space. This is called the Goerdelsen conjecture, and it's a prediction of string theory, of quantum gravity, sorry, which is consistent with what we know in string theory. In string theory, we also have no obstruction going from one to the other. The third criteria is that all the gauge charges appear in the spectrum. You cannot have Maxwell's theory with electric charges and let's say all the even charges appear, or no charges appear at all. It's impossible. So just the very fact that we have electrical field must necessitate having electric charge objects of all charges. As I said, without gravity, there's no problem. You didn't need to have it. But gravity says, no. If you have gravity, you better have charges. And what's the reason? Again, black holes. Black holes imply this must be the case. Because consider a big black hole of mass m bigger than the charge, then such a black hole solution exists. And according to the Wittgenstein-Hawking entropy, there's a huge number of them actually, huge number of states with that mass and that charge, given by the area of the event horizon over 4, exponential. And now take one of these black holes and take another one with charge q plus 1 and take the anti-version of this one, so minus q charge black hole combined with the q plus 1 charge black hole, combine them, and by charge conservation of the electric charge, you get charge, net charge 1 effect left over. And therefore, since these states are occupied by something, there's an entropy. The result of this is going to be some state existing in your theory, which is charge plus 1. And so if the elementary charge appears, then you can get, of course, full charges. So therefore, all charges must be there in the quantum theory of gravity, again, consistent with what you have seen in string theory. Finite range for fields. Consider a field phi and imagine it has no potential. It's flat, no potential. The potential for this field is 0. In principle, you would think that, okay, if you have a real field, it can take a value from minus infinity to plus infinity. However, even though this is perfectly fine without gravity, with gravity, it doesn't seem to work that well. Namely, it turns out that if you move in the field space by something which is much bigger than order 1 in time units, then your description should break down. In fact, in general, if you write down the action for these fields, you get a natural term in the action, which is related to the square of the gradient kinetic term of these fields, which naturally defines the distance on this space of the fields. And it turns out that what happens when you go to large values of this field space, the theory ends up being described by other theory. It gives a dual description of your theory. So for order 1, you can move around. But if you try to push it more, you can in principle, but that means you leave the original theory, you have a new description coming in. So you, within a given effective field theory, the range for the field is finite. And if you push it farther, even though you can, but that means you have a different description. So within a given description, the range is finite. And this is a reflection of string duality. What happens is that as you go far in the distances in field spaces, a tower of light states emerge whose mass goes down exponentially with the value of the field space. So you get a tower of light states always appear in your field. This has a potential application to our universe, actually. So this is the first contact I want to mention. What does it have to do with our universe? This is the first place. You see, cosmological constant, or what sometimes we refer to as dark energy, itself can be viewed as expectation of a field. In fact, in string theory, nothing is a parameter without being expectation of some field. So therefore, there must be a field whose expectation effectively characterizes the dark energy. Let me call that phi, and it turns out that if you want to have a natural metric on this space, you have to parameterize it in the form I have shown here, lambda is equal to minus phi. On the other hand, as I go large values of phi, I told you that I get the tower of light states, like here, n goes like e to the minus of phi. On the other hand, the value of the cosmological constant is very small, corresponds to phi of order 300 in time units. I said that of order 1 in time units, you're fine, but if you go more than order 1, you get a tower of light states. Therefore, in our universe, this is a very large number, and we should get a tower of states which go like the power of the cosmological constant. So we are immediately deduce just because the dark energy in our universe is small, there must be a tower of light particle in our universe. Now, this is a complete statement. A tower of light particles, where is that? Why didn't we see it in the CERN experiment or any other experiments or around us? If it's lighter than anything, where are they? So am I getting a contradiction or not? It would have been a contradiction if all the matter in the universe were the standard model. But is that true? You see, indeed, it turns out the only possibility is to combine this picture, this idea, with other idea observation, means that one of the dimensions of the universe should be bigger than the rest and related to the scale of the dark energy. And the light tower I'm talking about would correspond to the gravity wave in this extra dimension. So the extra tower of light particles are basically gravitons in the extra dimensions, the harmonics of graviton in the extra dimension, which happens to be large. And they will be weakly coupled, and they behave exactly like what dark matter would be like. Dark matter is weakly interacting with us. We don't know its mass, but it's perfectly consistent for it to be light. And we know they exist. Therefore, the smallness of dark energy predicts the existence of dark matter. So this unifies the dark sector. The dark energy and dark matter kind of become related because of these ideas in string theory of quantum gravity. So this is quite interesting because now we predict that our universe will be kind of a slice inside one higher dimensional universe. We cannot be extended ourselves into these other dimensions because if we were, then we would have a tower of electrons and a tower of quarks, which we don't have. And therefore, we better be like in a slice of this universe. And this would mean that if you consider gravitational attraction at distance scales smaller than this extra length, then you should be able to see the gravitational force law changing because the gravity field will pierce through these extra dimensions. And the 1 over r squared law, which is the one in 3 plus 1 dimension, becomes a 1 over r cubed force law in 4 plus 1 dimensions if the r is much smaller than the extra dimension. And the extra dimension can be estimated to be of the order of microns, and this would be extremely interesting to check. In fact, the current bounds on the radius of any extra dimension is about 30 microns. So we are on the verge of checking or ruling this out. If we can go a few order of magnitude down, then we can either see or disprove this point. And in fact, so this is potentially an extremely interesting experiment, just a simple power law change of gravitational force law. And actually, the experiment is being done at least by two groups, one of which is I'm showing here in Vienna, near a mine in Vienna, involving a rotating attractor and a pendulum torsion that measures it, separated by a Faraday screen to shield all the electrical field between these impurities and the surfaces. And you have this kind of thing, as you have the idea is that you have regions of high density and low density on the rotating disk, attracted disk. And as you go around, the different sides of the pendulum is attracted to one or the other, driven by the frequency of the attractor to focus on a particular gravitational force. And in this way, you can kind of check whether there's a 1 over r squared, 1 over r cubed force law or not. This experiment is not optimistic. Practically, it's very natural to expect you can go up to 10 micron distance at least from the 30 micron. Whether it can be pushed to 1 micron or lower, it's unclear yet. But certainly, it's an extremely interesting experiment being done. Now, I mentioned that, and this was a question that Abhijit asked, is can we explain why there should be extended objects in string theory? So here I'll try to explain that. So consider your universe, like in our universe, and imagine putting one of our dimensions, one of the directions in the space on a circle. Put it on a circle. So imagine that you compactify our universe, one of the direction, on a space periodic boundary condition, and change the period. So you write the radius in the form of a field, because after all, radius is dynamical field, and you can imagine making that radius smaller or larger. So you have a Lagrangian like this. Now, as I mentioned, if you go to extreme values of phi, you must get a tower-like state. For example, suppose the radius is large. What happens from the viewpoint of the lower dimensional theory is that you get a light tower of very low wavelength, large wavelength, or low frequency excitations of graviton. Those would correspond to light particle power in the low dimensional theory. On the other hand, imagine going to phi goes to minus infinity. So if phi goes to plus infinity, the state's energy 1 over r gives you the light state. But if you go to phi very small or negative, then the radius is going to 0. So in other words, imagine taking the radius of the universe in one dimension and shrinking it down all the way to 0. Then all the towers of these wavelengths of the things shrink and the energies go up. So therefore you can ignore all the excitation. So the theory seems to simplify and you don't seem to get any tower. However, the duality predicts that there must be something becoming light, the power. So what is the power which is light? You're identifying points of the space which are coming close together. So it's a non-local operation. You say this point and that point are glued, identified. And the only way that something can be sensitive to that getting lighter is an extended object which feels both sides. You need an extended object so to get light when you shrink it down. So extended object can have like a membrane or a string or something which is kind of wrapped around this extra direction, whose effective energy or mass is proportional to this length. And as the length shrinks down, the effective tension or mass goes down. So that would be the mechanism, and that's exactly what we see in string theory. The next criteria I mentioned is that the gravity is the weakest force. So it has been observed that in the context of solutions in string theory, when we have charges, the electric force between elementary charge states are always stronger than their gravitational attraction. Just like in our universe, if you have two electrons, their electric repulsion is far stronger than their gravitational attraction. In other words, m squared over r squared, the gravitational pull between, let's say, two electrons, is much smaller than the electric Coulomb potential, Coulomb force repelling them. We're measuring here m in Planck units, so there's no Newton's constant in the formula. So, in other words, m is always less than the electric charge in our universe. And it's also seen to be the case in all the examples that we know in string theory. Gravity is weaker than the electric force. So for the case of the electron, this is an extreme imbalance, namely the mass of the electron in the fundamental units is something like 10 to the minus 23, and the electric charge is something like 10 to the minus 1. Indeed, the mass is much smaller than 10 to the minus 6, less than 10 to the minus 1. So this is a feature we have seen in string theories in all of them, which is consistent with observation. But actually, we can explain that this is true not just in our universe, but in any putative universe consistent with quantum gravity, again, because of black holes. How does that work? Well, start with an extremal black hole with a charge equals to m, and imagine emitting a charge state, small charge state q with small mass m, as the black hole is evaporating. In this case, the charge goes down and the mass goes down, but you started with equal charge and mass. Therefore, for this, as I said, when they both go down, they should satisfy an inequality which allows for the black hole to exist. Mass is always bigger than the charge. So therefore, this charge should be lower than the mass. but originally they were equal. For this to happen, the mass of what you're emitting should be less than its charge. In other words, for the black hole to be able to evaporate, it better be that there are light states with mass less than their charge, just like in our universe. So the assumption that the black holes should be able to evaporate necessitates that there are states whose mass is less than charge for this process to happen, as it's in our university case. There's exception in what's called the BPS states in the supersymmetric case, which is the only exception, which I won't get into. But basically, this is true. There are further evidence for this weak gravity conjecture, the conjecture that gravity is the weakest force in the context of quantum gravity. So suppose you take pure Maxwell theory, no charge state at all. It turns out that if you couple that to Einstein's theory, you start with good boundary condition, initial condition with no singularities, and evolve. You can have a situation, depending on the configuration you set up, you run into singularities. And worse, you run into what's called naked singularities, which are not scoped by horizon. So in other words, you can see them at far to infinity, the effect of the singularity. And people have conjectured, like Penrose, that there should not be any naked singularities. So this will not look like a bad feature. Now, one could say, well, maybe Penrose's conjecture is false. It's not the case. It's okay to have naked singularities, maybe. But this was a bizarre feature. Actually, it turns out that these principles I told you already prevent this possibility. So let me explain how various ingredients come to fix this problem. First of all, I told you there cannot be a theory like Maxwell theory with no electric charge. There must be electric charge. Completeness of the charge in the theory. So there must be charge states like electron. Secondly, the charge object cannot be too heavy. Their mass is less than their charge. That's the weak gravity conjecture. Finally, when you look at this solution, when the electrical field became strong is when you got the naked singularity. But when the electrical field becomes strong, you create these particles in such a way to string the electrical field and diffuse the singularity. So precisely when you are about to find the naked singularity, it strings a dot. And in fact, you find precisely the condition m is less than or equal to q is sufficient to prevent this from causing a naked singularity. So in other words, Penrose's conjecture that there is no naked singularity is, what's called the cosmic censorship, is consistent with what we know in the context of quantum gravity consistency from a completely different viewpoint. So these again feed into a consistent picture without using string theory, but consistent with what we have seen in string theory.
So these are these calculations by Horowitz and
correct. Horowitz, but science. Yeah, exactly. This is kind of really reassures that the principles we're finding are self-consistent, they reinforce each other, and we believe more and more about them. And they're consistent with all the things that we are learning in the context of string theory. There's another application of the weak gravity to our universe. We live in a universe where the cosmological constant is positive. And we don't know if this is really a constant or it's evolving or if it's not evolving, how it's not evolving, but certainly we know that even if it's not evolving very fast. It's approximately constant. This kind of a space is called the de Sitter space. Positive cosmological constant. You can consider evaporation of black holes. I was talking about the evaporation of the black holes, and I explained why gravity is the weakest force arises by the evaporation of the black holes. However, I should have also talked about the condition of the evaporation of the black holes in the Sitter space where we live in. It turns out that if you consider the evaporation of the charged black holes, extremely charged black holes in our universe, for a black hole which can be as big as the universe, you get the new restriction in the opposite way. It shows that the mass cannot be too small. So that means the charged mass object has to have a lower value on the other side. So this is again follows from a weak gravity conjecture applied in this case to the de Sitter space. So you get an inequality on both sides. You have a bound for the mass of the electron. If you apply it to our universe, you find that the mass of electrons between 10 to the minus 1 and 10 to the minus 41.
What happens if it was smaller? You get a naked
You evolve that to next, and what happens is that you discharge through these light particles, and you go to the regime, and the black hole goes into the thin region of the allowed regions of the black hole, and you find that you're actually super extreme. So therefore, you get a problem. But this is interesting because the lower bound turns out to be very close to the mass of the neutrino. And it happens also to be close to the mass of the graviton excitations in the extra dimension I told you about, what I call the dark dimension. They're all kind of close to the neutrino mass scale. So this predicts that the mass of the electron is bigger than the scale, which in this case is roughly the neutrino mass scale, and 10 to the minus 1, which is a true fact about our universe. So this is a post-prediction, if you wish, but it could have been a prediction in the sense that the measurement of lambda predicts the value of the electron's charge.
The neutrino is not charged, so why is it relevant?
No, I call it neutrino so that you can place this scale in your mind what it means.
I see.
Not, you're right, that's nothing to do with neutrino per se, but neutrino scale. So I just want to say what scale this is. It's a neutrino mass scale.
Interesting coincidence.
I mean, it could be an coincidence or not, because that same scale is related to that dark dimension energy scale, which is related to dark energy. Same thing as why mass of neutrino is given by 1/4 power of dark energy. Might sound like coincidence, but we think it's not actually. So there are these coincidences that are appearing in quantum in our universe could naturally potentially be explained when there are only a finite number of possibilities, as this quantum gravity is trying to say, where it necessitates relations. So that's part of the point of this quantum program is to find what kind of connections between these things are there.
But it seems to pick out a specific time because this coincidence holds only today. The scale of the dark energy is set by h sub 0, not by h.
So the question is whether dark energy is evolving or not.
But put it another way, you argued that the scale is set by the big dimension, which is of order h0 inverse, corresponding light hour of states with this spacing of 10 to the minus 42 g, which is precisely the scale. But if you were giving this talk a billion years ago,
nothing would have changed. The mass of the neutrino doesn't change.
mass of the neutrino
Dark energy doesn't
but the
change.
dark energy scale would change.
No, dark energy, sorry, maybe we are having different. I'm not talking about the parameter h, I'm talking about lambda. The dark energy.
Lambda is of order h naught square. That is what
No,
you
that's not what I mean by dark energy. Dark energy is the constant portion of it, which scales with W is minus 1. That component of it is defined dark is not h naught. H changes, you're right, I'm not talking about it.
But the scale of lambda is set by h sub 0. not by h.
No. The dark energy becomes relevant only in the recent epoch.
Correct.
But H not changes. So therefore, but the dark energy presumably was there forever. It's not changed. Dark energy doesn't change.
I understand.
That's what I'm saying.
What you infer from observations is that lambda is of order h sub 0 square, not h square. Otherwise, he could just absorb it on the left-hand side.
Lambda today is of order H because roughly dark energy dominates. That's all.
Yeah.
But the idea that the state I'm making is not time dependent. The dark energy component was the same back in the early days of the universe, but it was not a major part of the energy of the universe, not major driver of the Hubble expansion. That's correct. I never said it was.
So if we discover tomorrow some major object of 10 to the power minus 3 electron volt mass, what are you going to say?
Then it would be a problem. If you had a charged object, which you mean on the other side?
Yeah.
Yes, I would say you would have big H in the statement. I'm saying you will not find something. That's why there's a prediction. Exactly. So this fights. If you find one, you have refuted this statement. And therefore, there's something wrong with my reasoning. But anyhow, this is the context. Predictions are dangerous, right? Preventing predictions precisely it means it can be refuted in principle. By the way, one other this, by the way, you can use this statement here to actually say something about the nature of the electroweak vacuum. for example, we have this level of potential with a maximum at the center of Higgs potential. You could have contemplated a situation where that maximum could be a minimum, a local minimum, like it goes like up and maybe a little dip down there and then continue. This says this is not possible. Because if you had that, you would find a contradiction of objects which would be charged and they would be violating this bound. So therefore, it does make predictions like that also. Are there restrictions on the critical points of V? Well, an important question of early cosmology, maybe in the context of inflation, if we assume there was an inflation, or late cosmology in the form of dark energy, is the form of the potential of this type as a function of fields when V is positive. So in the context of inflation, for example, a large region of flat potential is needed in typical and standard models of inflation for a field to roll over it before it settles to its minimum to give you enough expansion to explain the homogeneity in the universe. And when it settles, it should settle to a value of the potential, which we can call the dark energy today, which would potentially be the value we want. So a potential like this would have been something people dream about in terms of what could explain both the inflation situation as well as the universe today. Is this actually possible to get in string theory? Now, without string theory or quantum gravity descriptions, people usually used to say, sure, you just draw the potential and put that in your Lagrangian. What's your problem? What is the problem? In fact, that is the mode of operation in effective field theories. We have no problem. If somebody said you're not allowed to write it down, you would revolt and say, I can do whatever I want. I will just write down this potential. But we are learning that quantum gravity somehow is not consistent with everything you want. So the question is, this kind of potential that people draw and they love, is that really in the list of good ones or bad ones? That's the question. Now, before I say this, this turns out to be a very difficult question for in the context of string theory to address. Part of the reason is, whenever the potential is positive, you must necessarily break supersymmetry. And when you break supersymmetry, the analytic controls of the theory, we lose our analytic control of the theory, except for the weak values of the couplings, which is only a particular corner of the values. So for the bulk of the space, we don't have effective tools to analyze this situation. So if you go back to the space of fields that I was talking about, expectation value of massless fields, at far enough distances in field space, you get weak coupling descriptions. And at these corners, you can actually compute the potential, and you find that they go to zero exponentially fast, typically. So therefore, asymptotically in field space, you do not have a picture like this. In other words, if you go far to infinity, it cannot be this going up. But it has to come necessarily down. We cannot have a situation which stays constant or goes there far enough into infinity. The potential always seems to go down. This is an example of you cannot get everything you want. Goes to zero at infinity. In fact, more than that, we can actually quantify how fast it goes to zero. It turns out that if you normalize things in Planck units, the exponential rate in which it goes down is bigger than or equal to square root of 2 in log space. So this really goes down quickly to zero. In fact, with this value, you can show that this is too steep at infinity to allow for inflation. So if you want inflation, it cannot happen too far away in field space. It should be in the middle, perhaps, or something else, but not asymptotically in the field space. So could you have something like this then? At far in the infinity, you go to zero, and somewhere you get some metastable, let's say, de Sitter space, which is locally fine, and you could have something like this. Well, without saying whether this is possible or not, we immediately deduce, even if it were possible, it cannot be stable. It's metastable at this. So we are making a prediction. Our universe cannot be stable. because there's positive energy. That's it. So the dark energy being measured already tells you that our universe is doomed eventually, in some form or another. The time scale remains to be determined, but it's doomed in that form. Sorry to say, this is another occasion, but anyhow, I have to break the news to you. It's our universe is not forever there, because at best we are like this. Now you might say, okay, fine, it could be a huge bump. Hopefully, this bump is high enough. We don't have to worry about either my next generation and generations to come and so on. So it's possible. Let's just see whether or not it's the way it is. So as I said, we know that asymptotically the potential goes steep to zero with some sufficiently fast rate. But what about the middle? What can we say about the middle? Asymptotics are easy, the middle is hard.
So this seems to rule out a constant potential.
Absolutely, it rules
The
out.
first one is
Yeah. Constant potential is ruled out. Correct. That's fine, large enough fine, very close to zero. That's an example of the things that's known. You cannot say, oh, I just had a constant. So constant dark energy with flat potential has fine, it's impossible.
so that rules out like the cosmological constant.
Well, Kalmas could be a minimum of the potential, like that's what usually people think. They don't think lambda is a function of another field. But if you assume lambda is a function of another field and it's not varying, then yes, that's the problem.
If I just put a constant in the Lagrangian,
It's, if you just put the constant, which does not depend on the field, it could be like the minimum of here, approximately is true. There's a massive mode that you might be ignoring if you have such low energy, then it's fine. So the dark energy by itself could be looking like the minimum of this metastable decision. That's not a problem. The question is that if there's an extra field for which it's massive, that's a problem.
The bump is Planck and White. It
Yes.
could be a good model for inflation because that's exactly what topological inflation requires.
Having a what?
A Planck and White head.
You want more than Planck scale. Typically, in the inflation, you want like 20 orders of 20, whatever, depends on how many units you want.
That's right. So this was actually something Lender proposed. The outer parts would be unstable to slow roll.
Yes.
Central part remains topological.
Yes, so I will mention something about that in a second, but anyhow, so asymptotically you cannot have this. That's already surprising. Why can't you have asymptotic inflation? If you already could have drawn potential, there's no problem. But we're saying no. In string theory examples, we never see anything which allows inflation to function in order to find. Of course, this is not so surprising because typically the potentials you would imagine would be related to some power of mass. And if you have like power of masses, the mass is going exponential to zero, then you expect that, for example, the potential will go to zero exponential. So this is not that surprising, given the distance conjecture or duality. So duality in string theory also predicts kind of that the potential should go to zero. So the question about what happens in the middle is very tough, and we don't have a reliable explanation of what it is. There are various alternatives people have proposed. I'll just mention some alternatives. One alternative is that there's no restriction. It's just restriction is only at the boundaries. Well, this sounds a little strange. You would expect there should be some restriction if it's something in the boundary values are fixed in some particular very restricted form, which should imply something in the middle. But what? So this I don't think is true, but we don't know what it should be the inside necessarily. There is a conjecture that this asymptotic feature that we are saying is true everywhere, except possibly you can have a maximum, but not a minimum in the middle. And then there's a third possibility that is what's called a Transplanckian censorship conjecture, which tells you that you cannot have a potential in such a way that if you roll on it, you'll have a situation where the universe starts expanding so much, that it takes something very tiny scale, Planck scale, and making it bigger than the whole universe. Now, why this could be potentially true is that if you have something very tiny, smaller than the Planck scale, it should not be physical. We don't expect things which are smaller than the Planck scale to be physical on gravity. Whereas if you expand it beyond the size of the universe, it freezes in. And therefore, you will have it frozen in lower modes of the universe, which should not be physical. So this would be, it's at least a motivation of it. It's not a proof, but kind of a motivation. This is called the Transplanckian censorship conjecture. if you assume this, what you find, so if you assume this, you immediately derive this bound at infinity. Just transparent session congestion derives this bound, and moreover, it shows that bound that constant should be bigger than or equal to √2, which is exactly what string theory observes. So this transparent censorship conjecture gives you a value for the asymptotic growth of the potential exactly consistent with what string theory has observed. So if you look at these in the context of inflation, there's some tension because large field inflation is a little bit problematic because you typically get light states, and that light states mess up the Newton's field. You begin to generate this tower of light states. So that's one possible problem. But more precisely, in the context of Transplanckian censorship conjecture, if you assume this, and if you apply inflation to it, you find that the scale of the inflation is really low, if that's the case. And the parameters of the epsilon and the R that are some of the bread and butters of the inflation will be extremely fine-tuned. So it doesn't sound very mad. So it seems like if this conjecture is true, the inflation is going to be have to be replaced. And of course, there are many different ideas of what inflation can be replaced with, because after all, in the context of string theory, dualities are there. So if you push back our universe to the early times, the temperature goes up, and you would expect a different description to take over because it's a large distance in field space. In this case, the field playing the role of the temperature. Temperature could be viewed, inverse of the temperature could be viewed as the radius of the thermal circle. So going to the large temperature is somewhat like going to small circles. And you do expect a different description. So therefore, it is not surprising that something else should take over at early times, not necessarily a scalar field doing the job. So a dual description should explain potentially the problems that inflation solves, like homogeneity and all that. Could there be a totally different description of early universe in the dual dualities motivate one? In fact, in string theory, not having dualities in early universe is bizarre. It is fine-tuned. You should expect, it used to be it used to be a good feature to have a complete theory. String theory tells you that's a bug. It's not a good feature. There should not be a complete description over all regions of one single effective field theory. That description should break down somewhere. That is a good feature of quantum gravity, not a bug. And so this is a change of frame of mind that we should not be looking at a simple Lagrangian describing everywhere for all the regions of field space.
So, sorry not to, maybe I should wait, but that Transplanckian issue might also say that if you have a big enough black hole, it would stop evaporating at some point, because there is similar Transplanckian.
It's a different issue. Actually, there's a nice paper written by Ale Bedroy, which describes exactly what's the difference between there's what people call Transplanckian problem in the concept of black hole evaporation, and there are different issues there. So I think they're not quite the same issues. So now, present and future could be, you can ask what happens if you assume these conjectures. If you assume the Transplanckian censorship conjecture, it actually gives you an upper bound for our universe of 2 trillion years. So this predicts that our universe will decay at the latest a factor of 100 or so and more. So we have some time to guess if this is 200. Anyhow, either of these conjectures explains the why now problem. Why the timescale associated to the measured value of the dark energy is close to the current age of the universe. That's related to the fact that if you had measured that earlier, you would have a value. Why is it that today the dark energy matches the timescale? The timescale down relates to this value of the dark energy. In other words, why does the dark energy just happen to expand, just take over relatively recently in the cosmological epoch?
Sorry, this is the circular argument because lambda is, as I said, of order 8
No.
square.
I'm asking a different question. Suppose we live 10 to the 100 times later in this universe. We still measure the same number.
If we do.
If we do.
But
I'm saying that the question is, why is it that we're just measuring it today at this value instead of, so the time, there's a natural time scale associated to lambda, which is 1 over root lambda. Why do we see it now instead of 10 to the 100 times later? It could have happened then. We could have been living then and see it. Is it a coincidence that we're just measuring it now? That's a coincidence problem. It's a coincidence of, is it a coincidence that we did today or no coincidence that there's a reason for that? People naturally say, oh, it's a coincidence. You may have lived much longer and will not be true anymore. The claim is that if you believe what I was just telling you, they explain it's not a coincidence. Why is it not a coincidence? Well, the time scale associated to lambda is the same time scale that the energy will decay, the universe will decay. Therefore, a typical lifetime in such a universe is 1 over lambda. And so therefore, if you sample the universe in that dark energy one, you will find time scale that we're talking about. So there is no coincidence. So this is suggesting indeed as an evidence that the universe is bound is explanation of this coincidence problem. It's not a coincidence. So therefore, lack of the coincidence is an evidence that the universe is doomed in the lifetime scale, not too far from our brain. So, and I already mentioned to you that the distance or duality conjecture gives you a unification of the dark sector, and the light tower gives you the dark matter. So that's already an interesting prediction that one can try to check experimentally. Let me just see, I run out of time, so I have already mentioned brief aspects of this. So let me just conclude by one last, one or two more slides. One is that there's this picture that Dirac pointed out a while back. These strange numbers up here in physics. The ratio of things are huge and small and so on. Is this a coincidence or can be described in some theoretical fashion? It turns out that one can actually connect these through these Swampland principles that I told you about by powers of the dark energy itself. Dark energy is so small, and so simple powers like 1/3, 1/4, 1/12, 2/12, etc., give you vastly different scales. And indeed, we can explain these powers, even though I'm not going to have time to explain all these powers. It connects it to the various features that we have. For example, lambda is 10 to the minus 120, the dark energy today in time units. The age of the universe now, inverse, the Hubble constant is square root of lambda. The mass of the neutrino or axion or the dark matter, all the same of the order of lambda 312. The lambda scale of QCD and the weak scale is all lambda 212. The fundamental time scale in 5/5 dimension is 10 to the 10 GeV or lambda to the 112. And lambda to 0 is the time scale here today. So these tell you that maybe these funny numbers, which are huge but ordered in some form, is related to simple powers of this lambda. So there's only one fine tuning, lambda itself. Why lambda is so small? But the relative ones are no fine tuning. So let me conclude. Swampland conditions can lead to potentially observable consequences for particle physics and cosmology. Almost all quantum field theories are in swampland. And fine tunings, maybe such as hierarchy problem, may end up having a totally different solutions. With severe restrictions on consistent quantum gravity theories, and these ideas suggest restrictions on light matter fields, and positive energy puts a huge restriction on what is possible, and in particular suggests the existence of one relatively large and microscopic dimension, which we call the dark dimension. It's a fifth dimension. And one would expect that new ideas and dualities may be relevant for the early universe. Thank you.
You seem to be 100 microns, not 1 micron.
Sorry?
The scale of this dimension should be of order
Yeah, so
100 microns.
So
when you get
if you literally take lambda to the minus 1/4, you get 88 microns. Exactly.
Right.
But they're order one number, so here we are not putting them. We don't know those order one numbers.
So this is in your.
That's part of it. But good point. Yeah.
Thanks.
Exactly. Maybe just some time ago when I studied this one large extra dimension, the higher dimensional blind scale works out not too far apart from 18, right?
10 to 10 GeV. No, 1 or 2. If there are two extra dimensions, it's not very close to TeV.
I see.
But in fact, like 1 or 10 TeV or so. 1 TeV or 10 TeV, which is basically ruled out almost now.
Yeah, right.
But that's ruled out for yet another reason. Quick dimensions, the neutron stars. So that's but this is not ruled out. Yes.
So the dark matter that you talked about,
Does it have only gravitational interactions?
Yes,
It cannot
it's
have any other
It
interaction.
is graviton, literally graviton. So that's one of the nice features. You don't need an extra matter to call dark matter, gravity itself.
That's a prediction that it has only.
It's gravitational.
Does not have any other
No,
interaction with.
No, it's gravity. It's gravity.
So
It's
that's.
very natural, and it's therefore you're not going to see it. If this feature is true, direct detection of dark matter is going to fail.
Is there some estimate in your dark dimension model that gives you the fraction of dark matter?
Yes. So if you assume the Transplanckian censorship conjecture, meaning that the time scale in the decay, then you find you can then get a what you need is the initial temperature on our brain. Because what is dark matter is the graviton's extra dimension. What creates it is the temperature, initial temperature on our universe, which creates the graviton because it couples to it. Now, if I give you the initial temperature, you can predict the amount of dark matter it produces because of the universality of gravitational coupling to everything, including the energy momentum tensor on our brain. So therefore, you can predict how much matter you create. So your question in that context translates, can you predict the initial temperature on our brain? Now, if the initial temperature is bigger than the mass of the moduli fields, it won't settle down. So the initial temperature should be lower than the mass of the moduli field. But for moduli fields, you can make a prediction of their mass. It has to have settled down. And the decay rate of the moduli field goes like m cubed over m Planck squared because they're gravitational typically. And that gives you a bound on their mass. If you know that they should have decayed by Hubble time, which is our universe, it gives you that their masses of order should be about 10 GeV or so, 10 or 100 GeV. So therefore, the initial temperature should be less than for 10 or 100 GeV. And if you put that initial temperature of the 5 GeV or so, you get exactly the amount of dark matter. So the dark matter will come out right exactly with that assumption that they should have decayed in the Hubble time. So no fine tuning in that sense.
Any more questions? Yeah. Maybe a light question, low energy conserve the charges. How do people think about in the context of these conjectures?
No, there are approximate charges or exact symmetries. Like approximate ones, there's no problem. If you say exact ones, then we have to talk about those. Like we have, in fact, one of the features in our universe is there is no approximate exact symmetries other than electric ones, gauged ones, in other words. We have approximate symmetry like isospin symmetry and things like that, which is not exact. Those are fine.
I suppose condensed matter systems say directions of magnetic.
But no, you can imagine having a defect or a system with a global symmetry. That's not the problem. We're talking about the bulk of the universe. That's different. Which covers to gravity in that universe. That's not the same thing as a defect or a sample or something. We're not talking about.
So I didn't understand your argument that the whole charge lattice must be populated. Just suppose we only had even charges. The argument was to take a near extremal and the anti. So then you will have Q plus 2 and minus
Yeah,
Q.
so if you more precisely what happens if you have only the even charges, you find that there's a one form symmetry, which is Z2 value. So it's a little more technical, so it's not going to be explained by the simple black hole picture I said, but it's again no global symmetry arguments, but the global symmetry in the generalized sense, in higher forms.
Yeah, this is in relation to the Sandip's question about black hole evaporation and why the arguments about chemistry. So is there some simple one-line explanation of why that is different from the universe?
I'm sorry, why is what different from yours? I think
So you said that for the universe to go to small scale, so a new dual description comes up, has to come up. So, but you said that there is a difference from that situation to a black hole evaporation, to the endpoints of the black hole evaporation are different. And
I'm not sure I understand. I did mention that if you put the universe on a circle and if you shrink the circle,
yeah,
You have to have a dual description. That's what. But where's the connection with black hole I'm missing?
So if the black hole becomes, the.
Oh, but the black hole is not the whole universe. Just the black hole is a region, right? Is the black hole becoming small in a big universe does not refer to the winding states. So let me just review the argument. The idea was that if you put the universe on a circle, you can have these winding strings or membranes wrapping around and becoming light. If the black hole becomes small, there's nothing winding around the black hole per se. So it's just black hole evaporates.
Any further questions? Not, is there a hand on the